So the idea of this workshop is to present you and to learn you step by step how to master the double emulsion production. For that, I will first introduce myself briefly and introduce the team as well. My name is Adam Mezian. I'm working as project manager at Fluigent for droplets and particle application. And on the other side, we have Youn Vitry and Adrien Dewand from Sequoia Technology. And they are both technology lead encapsulation. And they have strong expertise in encapsulation of active ingredients inside single and double emulsion, the purpose of this workshop today. So I think it's now the time to start. So Adrien and Youn, I give you the lead.
Okay, welcome everybody. Thank you, Adam, for this introduction. My name is Adrien Dewand from Sequoia Technologies. I'm going to give you a very short introduction to the generation of double emulsion using the device called raydrop that we have developed at Sequoia. And just after this 5 minutes presentation, we will focus on the live demo. The raydrop device is made of a metallic chamber filled with the continuous phase, in which two inserts supporting glass capillaries are introduced on the lateral sides in such a way that the capillaries are almost in contact at the center of the chamber. A nozzle printed with a submicrometric resolution is fixed onto the tip of the injection glass capillaries. The input capillaries provide the core and the shell fluids in the nozzle, while the output capillary collects droplets. At the entrance of the output capillary, the continuous phase pressurized in the chamber is subject to a dramatic acceleration because of the change of section and squeezes the droplet phases flowing out of the nozzle, resulting in the formation of double emulsion droplets. The system presents practical benefits, actually. A producible fabrication technique because of the use of a 3D printed nozzle and alignment of the parts in the chamber based only on mechanical tolerances. A good observation condition through the two glass windows closing the chamber. A connection to the fluid reservoirs using standard fittings. The possibility to fully disassemble the device for cleaning. And finally, the possibility to change one insert if you want to change the nozzle or extraction capillary or both to modify the droplets size range achievable. The raydrop is easy to set up, as you can see on the scheme. 3 lines of a pressure controller are connected to 3 reservoirs. Each reservoir is then connected to a filter to avoid contamination of the device in series with a flow meter to measure the flow rates. The continuous phase is directly connected to the chamber, while the core and shell phases are connected to valves. The valves allow to control the sequence of introduction of the core and shell phase. This setup is fully implemented in the emulsification platform that you see on the picture and that you will see working in the following live demo. It makes the system easily and immediately ready for double emulsion production. At the output of the device, you can choose to collect double emulsion or to connect the system to a chip to perform sorting, analysis, or other operation. Okay, now what kind of double emulsion can we produce using the raydrop? Actually, water in oil in water, or oil in water in oil using the same device, because there is no coating needed, with adjustable shell thickness by adjusting the flow rates. We also demonstrate the production of microcapsule by polymerization of a shell in the tubing connected to the output of the raydrop. The result is monodispersed capsules with a solid shell and an aqueous or oil core in which it is possible to encapsulate molecules. PLGA, alginate, chitosan, and many of the shells of interest are, of course, made possible using the device. Okay, now I'm going to let the floor to my colleague Youn for the live demo. Thank you for your attention.
All right. Here you have a view of the platform emulsification platform, but I will start with the raydrop that you can see here. So you have the size. You can see the chamber, inlet and purge here and here for the continuous phase. And here you will have the entrance for the shell phase and for the core phase. And on this side, you will have the exit for the collection. On the emulsification platform, you can see So 3 pressure controller connected to 3 reservoirs. You have 3 inline filter to avoid any clogging of the system. You will have 3 flow meter on this side. And then you will have here 3 valves to start the process. Everything is connected to the raydrop that you can see here. And you will have then a camera and a light for the observation of the experimentation. And on the side, we have a binocular just to see the double emulsion. So to start the experiment, we first go with the continuous phase. We can set, the pressure will vary depending on the tubing that you use and the fluid also that you use. But we start with the continuous phase. Then we add pressure on the shell phase. So here, the shell phase is mineral oil with span 80. And for the continuous phase, it is water with twin 20 at 2%. Then I switch the valve here to start the flow rate inside the chamber. And you can see some oil moving. So I will increase the flow rate of the shell phase to flush the remaining water and oil that was in the nozzle. All right. So now it's clean. You have oil all around the chamber, so we can decrease the flow rate of the shell phase. And we can start to add pressure. A bit less, a little better. And then we can switch the valve for the core phase to generate double emulsion. And in the core, we have water with fluorescein to help to see the double emulsion formation. So what you see here is that the shell phase is not strong. The flow rate of the shell phase is not strong enough, I would say. And so it will break the double emulsion formation, but it's not a problem because you just have to adjust both flow rate of the shell phase and the core phase to have the desired double emulsion. And to help also start again the process of the generation, you will have to stop the core phase here with the valves and then start again, and it will start again. And so now we can collect. We just have to wait a few minutes still so that the double emulsion goes through the wall tubing of the outlet, and then we'll be able to watch them under the binocular. And if you have a question or you want to see something again, we can do it again.
Okay, there is a question. What is the lifespan of the nozzle raydrop chamber? Okay, actually, if you use the system as we recommend, there is no date of peremption, I would say.
For now, we didn't find
Yes.
any date of peremption.
Yes, there is a list. We have a list of solvents that we can use in using the system, because the nozzle will not resist to all the solvent, but it will resist to a lot of solvent, to a lot of fluidic phase. But if you use correctly the system, there is no determined lifespan actually, because all the material used in the system are very strong. It's stainless steel, it's the glass, it's resin for the nozzle. So actually, there is no problem if you use the system in the correct way, I would say. Okay, there is a question about the maximum throughput we can achieve with the raydrop. Okay, depending on the geometry of the system, the geometry of the system will impose the size, the range size of the droplets. We can change the nozzle, we can change the output capillary to change the size range, and then the throughput, the typical throughput, we can go from a few microliter per minute to a few milliliter per minute, depending on the system. And in frequency, okay, depending on the size of the droplets, you can go through 1,000 kilohertz production of droplets. But this device is okay, is dedicated to the lab, to R&D, so it's limited to a few milliliter per minute in the best condition using an adapted geometry. typically you will work with a few hundred microliter per minute using this system to screen formulations and so on.
So there is one question regarding how can we scale up the batch size using this technology. So we are working on a device that will combine multiple channel inside in one device. So you have 10 times the production of a raydrop inside one system. So it is working for the simple emulsion raydrop, and we are working now on the double emulsion scale up.
Do you adjust the flow rate or the pressure? Actually, we can do both. Here we can play with the pressure and we measure the flow rate. But maybe Adam can add some information.
I can show it here actually.
Yes.
Actually,
okay.
So with the Fluigent system, so here I am only in pressure driven mode. So I will increase the pressure inside the system, and it will change the size and the shape of the double emulsion. But I can also click on the arrow, I would say, to start working with fixed flow rate. And so I will do this on all of them, and now I can increase directly the flow rate that is given by the flow unit, and it will interact on the pressure. So it will directly interact with the pressure in the pressure controller, and I can do it for all the phases. It's really useful when you are working in a continuous way, so that the pressure control the software will adapt to the pressure that the flow rate are the same. But in my opinion, when you start the system, it's better to work with the pressure because it's more reactive.
Exactly, yes. So we have developed an algorithm which, based on the flow rate measure, adjusts automatically the pressure. So you can control directly the flow rate as Yoon presented. But he is right. Using with pressure at the beginning of the system, when you are priming your system, is better because you will have a smaller response time. So you will be able to generate, to flush easily, to generate the droplet that you want. And as soon as you reach, let's say, a steady state, you can switch into the flow rate control to have a continuous production.
There is a question about the distance between the nozzle and the collection capillary. How do we make to ensure a uniform distance? This distance is guaranteed by the process of fabrication of the system. And okay, this distance is fixed, but playing with you have a small freedom to adapt this distance, because you can press the screw a little more harder, and then you can adapt for a few microns this distance. But basically, this distance is fixed by the process of fabrication of the device. But this distance is not critical. If you change the distance of 10 microns, it will not affect drastically the droplet formation.
The question is, what is the smallest size of the core droplet? It's not an easy question because it will always depend on the fluid that you use. If the shell phase is viscous, you will be able to achieve smaller core droplet than if the shell phase is less viscous. And I would say it was around 40 or 50 micrometer with the configuration here with the output capillary that you see in this demo. But if you use two nozzles, one in front of another, you should be able to decrease the size of the core. But I don't have any specific data in this configuration. It's something that I have to work on the next months.
The next question is, what happens if I manage to clog my nozzle? That's a bad idea to clog the nozzle, but okay, that's something that happens.
It's always happened. Yeah.
Yes. So if you clog the nozzle, you can try to flush from the inside of the chamber to make the fluid go through the nozzle by pushing the clog. If it doesn't work, you can immerse the system, not open the system, but immerse the system in an ultrasound bath. It works very well. And maybe try to fill a chamber with the solvent that dissolve the clogging. Yes, usually there is no clogging that we cannot remove. there is always an easy way to remove the clogging.
Yes, except there is polymerization
Yeah.
that is not deletable, but that you can dissolve the polymer. But yes, the first thing to do is to use the continuous to plug the output of the raydrop. So this side of the raydrop, you plug it and you flush from the inner part of the chamber to the exit of the inlet of the nozzle. So really, you flush backward inside the nozzle, and most of the time you will unclog the nozzle.
Yeah.
And if it doesn't work, you can use an ultrasonic bath to help this.
Most of the clogging comes from small particles or dust, and in this kind of particles is not it's easy to remove. But okay, dramatic situation is when you clog your system with polymer. But if you are working with this kind of product of chemistry, there are strategies to work with this. Using valves, you can first prime the system, initiate the system with the solvent without the polymer, and then when you get droplets, you switch to the solvent with the polymer. So you initiate the droplets without having clogging, without having troubles, and then you switch to the droplet formation. And after the droplet formation with the polymer, then you switch back again to the solvent to be sure that there is no remaining polymer inside the nozzle. So this way we can ensure that there is a safe production of double emulsion with chemistry that can polymerize actually.
And regarding the second question, so to change the size of the capsule and not just the shell width, do we need to change the nozzle, or can we also play with the flow rate or pressure? Of course. So if you want to change the size, you can increase the continuous flow rate, and it will decrease the size of the capsule. But you will always have to play a bit with the different flow rate to have what you want. It's not only playing with one flow rate that will give you what you want. You will always have to adapt the three, the continuous phase, the shell phase, and the core phase. But most of the time, the continuous phase will give you the size of the capsule, for instance. So a lower flow rate will give larger capsule. For instance, so I decrease the flow rate here, and it will increase the size of the capsule so that you can see it on the screen, I think. And if you increase, yeah, maybe I have to increase a bit the core.
Or maybe you can just switch in pressure because you are in flow rate control.
Yes, that will be easier for me. I'm used to work with pressure actually. But so if you decrease the pressure like this, so you'll be able to produce larger droplets, also larger emulsion. And if you increase the flow rate, you will decrease the size of the double emulsion. Of course, when you are in pressure mode, you have to compensate the decrease of the flow rate for the other phase.
Okay, but in the geometry of the system, so the size of the nozzle and the output capillary will constrain the range of size achievable. But if you want to change the range, so in this case, we can go from 80 to 150 microns. Yeah. Using this geometry. But if you want to change of range, so go smaller or bigger droplets, yes, in this case, you have to change the nozzle and output capillary. And okay, there is another question about the alignment of the nozzle. Maybe we can go back to the presentation, because this question is related to the one of Robin. There is the raydrop is made of 3 parts. The main chamber filled with the continuous phase, and there are 2 inserts. One insert supporting the nozzle, and one insert supporting the extraction capillary. So if you want to change the geometry of the system to go to another range of size, you just have to change these 2 parts. And for the question about alignment, the alignment is immediate. So you introduce the 2 inserts. And then you have the alignment. The alignment is just obtained due to the mechanical tolerance. So you don't need to make something tricky to get the alignment of the system. There is a question about the efficiency of the system in low temperature. Yeah, it's possible to work with low temperature. It will affect the viscosity and other properties of the fluid, but okay, you just need to adapt the pressure, flow rates, and the tubing to this viscosity. But okay, it's just a question of viscosity, and
cooling down the raydrop also.
Yes, and you need to cooling down the raydrop so you can introduce a cooled continuous phase. Huh?
Yeah, but also a Peltier element on this, because as the raydrop is in stainless steel, it will conduct the heat, and so you can use Peltier element if you want, for instance, to cool down the raydrop and ensure to be below 4 degrees.
Or heat, actually.
Or heat, yes. Or you can also use an air conditioning room. I mean, not room, but environment that is really cold.
High temperature, yes, it's also working very well. We have data with using resistance connected to the metallic body of the raydrop, and we heated an oil at to 90 degrees. Yes. And or it is necessary to use a surfactant in production of droplets.
So the answer is no. We are able to produce double emulsion and droplets without surfactant, but the stability area is really thin, and they won't last long. They will not explode, but breaks. Breaks during the exit capillary.
The shell is less robust, actually. If you don't use surfactants.
Yes, it's not robust at all, because you have a density mismatch. So the core phase, for instance, will go through the shell phase, either at the bottom or at the top of the double emulsion, and there will be nothing to prevent this. The surfactant are really here to prevent this not extraction, but this exit of the core droplet.
That's a good question, because actually we use the same system, the raydrop, to produce simple emulsion with another nozzle, just a simple nozzle. And in this case, there is no need to use surfactant to produce the droplet. It works very well without surfactant. But of course, actually, if you want to collect the droplets and have it for a long time, yes, sure, you need surfactant, but not for the production in simple emulsion. But we see that in the double emulsion, the process is more stable at the production with surfactant. Yes. Can you tell us about which polymers have you used? Okay, we have experience. We have a case study with alginate and with UV polymer that are not commercial. We have a partnership with a company that provide us some metacrylate polymers with a photo initiator. And then using UV lights we use UV light on the output tubing, and at the end we obtain a solid shell. So it's just a flash of UV on the droplets in the tubing, and that makes the shell solid. Yes, we also have experience with PLGA in the shell, and then by solvent extraction in the shell phase, the PLGA precipitated, so you have a solid PLGA shell on the particle. Yeah.
We also have the same case study with single emulsion with agarose, alginate, PLGA again, the same resin. So for both single and double emulsion.
We have no data with agarose, and I have no data with agarose and ketosane, but I think that it should be possible. Agarose. Yeah.
Some customers actually already use the raydrop for that, for agarose.
Yeah.
So yeah, it's possible.
The nozzle is a resin. It's made of a resin. Metacrylate resin.
Yes.
So yes, does that count from some liquid? There is limitation. Yes, of course, there is limitation, because this resin will not resist to all chemicals.
It's
okay. So you see the compatibility chart. So we tested a lot of chemistry, And what we observe is that some solvent will, the nozzle will not resist to some solvent for the long run. For the short run, it will also work. So you can work from 1 hour or so and so on. And then if you clean the system, if you completely clean the system, so you avoid long-term immersion, it can work. But for the long-term run, we don't use dichloromethane or toluene or DMSO because it will not work.
Yeah, what we saw is that either this kind of solvent, the not compatible one, either they will break the nozzle or they will dissolve it.
But why are we using a pressure controller and not syringe pump? Okay, in this case, we are using pressure controller because the answer of the modification of the pressure is very fast. So we can very easily fine tune the system, the shell thickness, and there is no delay between the information you send to the system and the answer of the system, the response of the system. So the system is very fast to respond. That's a good point of the pressure controller. And the second point is that we can use a big container. That's not possible with, that is not possible. Young, there is an issue in the formation. Can you just
decrease the flow rate of the core shell?
Well, it sometimes happens when you have an unbalanced flow rate. So to correct this, you just have to stop the core phase so that you regenerate a clean shell phase, and then you can add again the core phase. And maybe in this case, I have to decrease a bit the core phase flow rate.
So to go back to the question, of the syringe pump. Okay, so there is the answer is fast with the pressure controller, and we can work with a bigger reservoir. In using syringe pump, you are limited to the size of the syringe, so you cannot work all day with this system. Maybe Adam can add some information about.
Yes. This is so the two main points, and there is also another point that we have noticed is that as syringe pump are using mechanical action, you have some instability, small instability. You do not have a real constant flow rate. Actually, you have some pulsatile flow rate, which when you are making the single emulsion and double emulsion, can generate some difference in terms of droplet size. Small difference, but that which leads to a certain bigger polydispersity. So in droplet microfluidics, it's really important to have a stable flow so you can generate highly monodispersed droplets. And double emulsion also is the same.
Now the question why there is no need for surface treatments. That's because the system have a cylindrical geometry. So there is no contact between the droplets and the wall of the output capillary. So there is no wetting issues. If you are working with a traditional glass chip, in this case, there is always contact between the droplets and the wall of the system. So you have to apply coating to avoid wetting. But in this case, due to the geometrical, the cylindrical geometry, there is no need for surface treatment. We can do both tip of emulsion using the same system. We never applied coating.
And for the question for dioxane, we never used it. If it's of the family of hexane, it should be more resistant than in the case of toluene. But we have to do a specific test to ensure that it is compatible.
Yeah, if you have specific need, we can make a fast test to see if the nozzle is resistant to your solvent. That's possible.
For the monodispersity question, yeah, for both droplets, the monodispersity is below 2%. And to achieve this monodispersity, you need a precise flow rate.
There is a question about the highest frequency for generation. The frequency will depend on the geometry you're using. In this case, the droplets are approximately 100 microns diameter. So in this case, we can go to kilohertz droplet generation. But okay, if you change the geometry, you want to work with another nozzle to make let's say bigger droplets. your flow rate will increase, but of course your droplet will be bigger and the frequency will decrease. So, okay, frequency is interesting, but a more interesting point is the flow rate actually.
About the pressure range and the flow range that you can apply. So the raydrop can withstand a few bars. I think we tested until 6 or 7 bar, and there is no issue with it because it's stainless steel and glass, so it's resistant. And the flow rate apply will depend on the fluid actually that you use, and the size also of the droplet generated. But if for the continuous phase, which not really relevant, but we go up to 1 milliliter per minute to generate smaller droplets. And for the core phase, I think in this range, we go up to 30 or 40 microliter per minute, but it will depend on the shell phase that you use. The 40 microliter per minute were achieved with a desurf as a shell phase. And desurf is HFE oil with surfactant from Fluigent.
The question is, do you use any surfactants? Since I see there is no merging of droplet, they are very stable. For how long they are that stable?
Yes, so in this setup, I use, for the continuous phase, I use water with twin 20 at 2%. So it's a standard surfactant. In the oil, it's for the shell phase, it's mineral oil with span 80, I would say, that we use at 2%. And for the core phase, it's water with fluorescein, and I add also twin 20 to see the influence. But in the core phase, it does not really influence the stability of the double emulsion. What will really increase the stability of the double emulsion is the surfactant that's used in the shell phase. And so, for instance, the desurf emulsion, the double emulsion produced with desurf as a shell phase was the most stable that I did, and it lasts hours. But you can use other surfactants, and it can increase the stability or decrease the stability. It really depends on the surfactant that you use.
So there is a question about the high viscosity. It's possible to work with high viscosity. The highest viscosity we worked is alginate 2%, so it's quite viscous in the shell phase. But yes, you can work with higher viscosity. It will depend on the possibility to apply the pressure. Yes, because you apply pressure on the system, and if your tubing are adapted, you can get the flow rate you want. But too high viscosity will mean that the flow rate will decrease actually.
Yes, and the ability also to filter those liquids, because there is a restriction in the nozzle. I mean, the smallest dimension are at the tip of the nozzle, and so if you don't clean your fluid of particles, you might clog the nozzle. It's not really an issue because you can unclog it, but it will be an issue if you are not able to filter your solution because your solution are too viscous. So there is no real limitation on viscosity, but it's more on a practical use. If you are not able to filter them, for instance, it will be really difficult to generate double emulsion.
But actually, yes, we have data with viscous fluids as shell phase, polymer, UV polymer, or alginate. Yes, and it works very well. Yes. Question for you?
Yes. So there is a question on how I connect the tubing to the droplet generator, and I will switch to this camera. Yes, right here. So actually what we have on the radar, because we find the same issue as you in the past, and we were kind of annoyed by that. So we use really standard connection. So it's 1/4/28 thread, and it will reuse standard upchurch connection with 1/16 tubing, for instance, here. Or you can also use here on this side, we use 1/32 inch of tubing with sleeve, with adapting sleeve inside the raydrop. And you simply screw them, actually. It's really something like this. You screw, and it's done. It's really standard connection because we don't want to have something that is proprietary and that is troublesome to use.
And when if you are buying a double emulsion, the raydrop double emulsion, it comes with a kit, connecting and tubing kit, where you will have that type of connectors and also the tubing required to make the double emulsion production.
What is the smallest size of droplet we can generate with this system? That's a good question. We have a slide on this topic. Okay, as I said, using the standard system that you see in the live demo, the range is from 80 to 150. You can play within this range by playing with the flow rates. But if you want to change the range achievable with the system, you have to change the geometry. So changing the geometry means change the nozzle and changing the output capillary. But there is a limit. If you work with an output capillary too small, you will get very high pressure drop. So it's not possible. So what solution can we propose? As you can see on the slide, we put an output nozzle in front of the injection nozzle to locally increase the shear on the dispersed phase without increasing this pressure drop. So using this system, we are able to produce double emulsion with size less than 80 microns. The smallest size was 50 microns, yes.
50 microns. And we will work in the next months to decrease again this size to go up to the 30 microns. Because I think there is a lot of requests for this side of double emulsion.
There is another good question, actually. Why did you select co-flow geometry, not other configuration like T-junction or flow focusing? Just to get rid of surface treatment, or there are some other reason? Because fabrication of co-flow is more difficult than flow focusing, and with co-flow it's harder to go smaller size.
Yeah, actually, why do we make this system? That's yes. When I was in a lab at the university, I worked with traditional PDMS or glass chip, but with some solvents or some chemistry, I didn't succeed to make droplets in this traditional system. So I made the raydrop to avoid this system. And that was the only system that allowed me to make the droplets with my chemistry, because I never got wetting issues with the traditional glass chip. I damaged the coating within 10 or 20 minutes, so it was not possible to produce droplets. And using this system, we never got wetting issues. That's the first reason why we developed this system. And as you can see in the literature, there is a lot of publications using co-flow system, but these systems are made in lab using glue, using glass plates and syringe needles. It's not very easy to set up. In using this system, the implementation is more easy, and you can make a double emulsion, what is more tricky using co-flow lab-made systems.
And here we have bubbles that should come from where? There shouldn't be any bubbles, but it's okay.
Actually, it's a good example of what can happen using microfluidic. Usually, it's the managing the air bubble that could appear. As we are micrometric scale, air bubble can destabilize the system. So for that, there is optimization to do. What we are currently doing is degazing solutions, as Adrien and Youn said. But there is also, for example, if you are working on production and you are working on really routine experiment long term, there is also options such as degazing module, inline degazing module used in HPLC, for example. This is some module that we can also hide and develop to help have good reproducibility. Okay, so thank you everyone for your attention. And if you want to have more information, feel free to contact Fluigent. We can organize separate discussion on your application, on what you would like to know a bit more about our project. And and we keep in touch then. So thank you, everyone.
Thank you very much.